Good morning, ladies and gentlemen. May I have your attention, please? Let's go ahead and get started. So we need to be able to solve a differential equation that satisfies the given condition. And we've seen how we can find a general solution, right? If we can separate the variables, that is, get the independent variable and the dependent variable on opposite sides of the equation, integrate both sides, right? And then solve for my dependent variable. That's a general solution. One step further would be then to plug in the given condition, right? That data point to determine what that unknown constant is. So now you can use that exact solution curve to do things like make predictions, and that's much more useful. So let's go ahead and begin. Is this equation separable, right? Is this differential equation separable through a multiplication or division? Marissa? Yeah, we could divide over the y squared and multiply over the dx, and so certainly this is separable. We'll go ahead and do that in our first step. So dy over y squared. I'm going to go ahead and just leave everything else over here. I'm going to leave the negative, the 2, the x, and we'll multiply over the dx. Awesome. After we've successfully separated the variables, we'll go ahead and integrate both sides. So we'll integrate both sides. On the left, an antiderivative, right? An antiderivative for dy over y squared. Is that natural log? Natural log of absolute value y squared? No, good heavens no. Right? Just because there's a fraction doesn't mean we'll be using natural log. It's only appropriate to use the natural log as an antiderivative when we have a quantity on the bottom to the first power. And as you see, we've got a quantity on the bottom to the second power. So this is just a power rule, old school, right? We'll add 1 to the exponent, divide by the new exponent. So we should be getting negative 1 over y for an antiderivative, right? Negative 1 over y equals, and on the right-hand side, again, power rule. This time we'll add 1 to the exponent, divide by the new exponent, and cancel out that 2. So I'm getting negative x squared plus c. Recall that when evaluating an indefinite integral, a constant of integration is always produced. However, we decided now collectively to group that constant over on the right-hand side, the independent variable side from now on. As we saw, a constant that we don't know minus another constant that we don't know still gives us a plus c constant that we don't know. All right, now we can go ahead and solve for my dependent variable. So I can do that a couple different ways. I could take the reciprocal of both sides so long as I include quantity that. Or I can multiply the y over and divide over by the negative x squared. So we've got lots of different ways we can do that. So we could multiply the y over and divide by the quantity negative x squared plus c. Or we could take the reciprocal of both sides, so long as you take the reciprocal of the entire right side. That would be quantity negative x squared plus c all over 1. So the reciprocal would be 1 over quantity negative x squared plus c. Divide by a negative. And when I divide by a negative, right? When I divide by a negative, I could put a single negative on top. Or I could distribute that negative through the bottom. When I distribute a negative times a negative x squared, I get a positive x squared. When I distribute a negative times this plus c, I still have this plus c. How come the sign on that plus c didn't change? Well, you certainly could change it if you'd like to, but recall, a constant that we don't know multiplied by negative 1 is still a constant that we don't know, either positive or negative. And so I'm going to go ahead and let the initial condition determine what that c is. Once again, I've divided by a negative, right? Both sides by a negative 1. I've distributed through the bottom, and that changed the x squared sign, but I'm just going to leave it as a plus c because it's still a constant we don't know. Is that okay? Is everybody okay? All right, let's go ahead and use our given condition. We know that y equals 0.25, all right, y equals 0.25 when x equals 1. When x equals 1, is that right? So it looks like y equals 0.25 or 1/4 when x equals 1, so it looks like 1/4 equals 1 over 1 plus c. So through inspection, right, we can see that c must be 3 in order to make that true. Or we could flip and we could solve and we could subtract or however we want to do it. But is everybody getting c equals 3? C equals 3? All right. So now we're not done until we rewrite. We've determined that constant, that unknown constant, and now we have to rewrite with our given value of c. It looks like y equals 1 over x squared plus 3. Awesome. Raise your hand if you got that. Did anybody go into y equals 1 over x squared plus 3? Just a sprinkling. Okay, so what happened? Was it natural log? Was it natural log? You can tell me. Okay, so that's important, all right? That's important. That's a good mistake to make right now. We only use natural log as an antiderivative rule if it's a quantity on the bottom for the first power. What keeps this from being an antiderivative natural log? What keeps this from being a natural log antiderivative? Riley, E?
Because there's not a quantity on the bottom.
What's the quantity on the bottom? Y squared, right? To the second power, so that's just a straight power rule. Just a straight power rule. Daniel Kennedy, a longtime serving member on the AP steering committee for AP Calculus AB, listed universal logarithmic antidifferentiation as one of the top 10 student errors made by students on the AP Calculus exam nationwide. So anytime there's a fraction, he's saying universal, all right, logarithmic antidifferentiation. He's saying anytime there's a fraction, students want to go and do natural log, right, to integrate. Anytime there's a fraction with a variable on bottom, they want to do natural log. That's not the case. It's a top 10 student error because lots of people want to integrate that as a natural log rule. Recall that that quantity on the bottom must be present, must be to the first power. Furthermore, the derivative of that quantity must be present, right, in order to use the natural log as an antiderivative. And so make sure you're on the lookout for that, and that's a perfectly fine mistake to make right now so that we don't make it again. So that's going to show up again, for sure. Michael.
So when do we know to plug in the y?
To plug in that initial condition?
Yeah.
You may choose to plug it in as soon as you anti-differentiate and generate your dependent variable with no more dy's or dx's, or you can solve and find the general solution, as I've done, y equals, right? So solve for the, and then plug it in last. The choice is yours. Technically, you can do it anytime after you get rid of the, anytime after you anti-differentiate, so long as then, once you find it, you plug it into that same step before you plug it in, and then solve for y. So I typically go and solve for y first, solve for c, and then I just rewrite. I don't have to do any solving steps afterwards. You're welcome to plug in right away if you like. You may get a different value of c at the time, but by the time you rearrange it and solve for y, you should get the same exact solution curve. Does that make sense? Awesome. What questions do you guys have on today's Bellwork? Okay. Let's take care of our OTL number 2 check, and then we're going to go ahead and get your test back. So what I'm going to do is pause the recording now, and then after we're done with our tests, then we'll go ahead and resume the recording and investigate slope fields. During today's activity, I'm going to come around and I'm going to give you a manual program upload, and this program is called Slope Feed, which is short for slope field. You need your graphing calculator, and when I get close to you, you're going to press second, link, select receive, and press enter. Your calculator should say waiting, okay? So you can wait until that happens. If you do it now, it's just going to end up spinning and then say an error, quit after a while. So you can wait until I get close, but these are the commands that you'll be using. Second, link, receive, enter, and I'll say waiting. That has to occur before I can transmit the program to you, and so make sure you have your graphing calculator at the ready for that. Today you can earn up to, yes, that's right, 4 stamps during your activity, up to 4 stamps during your activity, 6B, 8C, 10C, 11C. If you go ahead and give yourself a little circle on the stamped eligible items now. I'm going to go ahead and get the iLink cable and record your Infinite Campus scores, and I'll come around. Please be ready when I get to you because we've got lots of uploads to do. I want to make sure that everybody gets this program, not because you need it today, but because you need it for next class, okay? And so if you don't have your graphing calculator, make sure you bring it for next class. You will need your graphing calculator and this program for next class, but for right now, I just want to make sure during the activity I get everybody uploaded. Does that make sense? Awesome. I'm going to go ahead and pause the recording. Let's scooch into our groups. Please be ready. Okay, ladies and gentlemen, let's go ahead and share our responses for our closure today. Again, 4 main ideas that we investigated in our 7-4 slope fields activity. Given a differential equation, how does one construct a slope field by hand? So what do we do procedurally to construct a slope field by hand? Right? How do we make that slope field? What do we do? James?
So you plug in the points and then you find the slope and then you draw a tangent line at that point.
Absolutely. So we plugged in ordered pairs to my differential equation, evaluated to find individual slopes, and then drew in many tangent lines at the indicated ordered pairs. And so we evaluate the differential equation at ordered pairs, right? And then we drew the mini tangent line that we got for the slope value.
Thank you.
So we can evaluate our differential equation at several ordered pairs, see what slope values are produced, and then draw a mini tangent line at each ordered pair with that slope value. Second, what's needed in order to find the particular solution to a differential equation? So what do you need in order to find a particular solution? Kobe?
You need a point on that, or a point to input into the equation.
Absolutely. You need a point that satisfies that solution curve. You need an initial condition, x comma y. You need an initial condition, a point. And notice how the word initial here, right, doesn't necessarily mean when x equals 0 or when time t equals 0. It doesn't mean initial value the way that we think of initial value being for an exponential equation being the y-intercept. It does not have to be the y-intercept. It just needs to be some known point, ordered pair x comma y that satisfies the solution curve. And that'll allow us to pin down that unknown constant. How does one estimate the solution curve to a differential equation graphically? Oh, I can't wait to call on Marissa.
I won't follow the signpost.
Absolutely. So you're going to go ahead and start at your initial condition point, x comma y, and extend the solution curve in either direction following the mini tangent lines as signposts, right? You're going to pretend like you're dropping the leaf in the pool and you're seeing where the current takes it. So how do we do? We'll start at our given condition, x comma y. And we'll draw the solution curve by following the direction of my tangent line signposts. I think I'm going to put that in quotation marks. Follow the direction of our mini tangent line signposts. That's fun. You're fun. Keep in mind, these aren't stop signs. These are go signs. You know what I'm saying? They're trying to tell you the direction you should go with that solution curve as you continue. And it's an imperfect science, right? You're estimating with that solution curve, but we should all share some things in common. A good general rule is that you want to be parallel to the nearest mini tangent line. You want to be parallel to that as you go and sketch your solution curve. How does one find the solution curve to a differential equation? Algebraically, right? So now not graphically, but algebraically, how do we determine the solution curve? Right? What words do we do algebraically? Hayden?
Integration, algebra with initial equations for constant.
Yeah, I just want to make sure we do the first things first is make sure that your variables are separated first, then integrate, and then plug in your initial condition to pin down that particular solution. Good. So we want to make sure we separate the variables. Integrate. Plug in initial condition. And rewrite with your C value plugged back in, solve for y, right? The variable solved for equals. Awesome. Great work today, you guys. What questions do you have about our closure? Then I'll go ahead and pause and save the recording, and you're welcome to pack up and visit for the last minute of class here.